So for this talk, we're going to discuss dead stars. I know, great dead stars. They're stellar remnants, if you will, or dead stars, or highly evolved stars, or extremely old planets, if you want to use the word planet and refer to the luminous objects in the night sky as being very young planets like the sun. The words can be flip-flopped around, moved around, reorganized. That's fine. The big problem is separating the two, thinking that the two are mutually exclusive objects, but they're not. The planets, as we understand them, are very, very old stars. These are dead stars. Earth is about 4.5 billion years old. Venus, I have about 450 billion years old. Mars, between 20 and 30 billion years old. Mercury, I have around between 7 and 32 trillion years old. It's extremely, extremely old. And then the moon, probably possibly older than Mercury. But I think the moon gives the appearance of being extremely old, but I'm not too sure if it's older than Mercury. I need more measurements to take. It does have a lot of craters though, so there's that. Notice how big Mercury's inner core is compared to the Earth. Look how big that mamma jamma is. So it's had all that time to ablate away its outer crust, its outer mantle, even though the core is about the same size as Earth's, which is really, really, really cool. For this talk, stages of iron absorption and deposition in a star. When a star is really hot, big and bright, it can collect a lot of iron. It doesn't start out with all the iron when it's first born, I don't think. But it just collects the iron over time because it has a very large gravitational field and it has a lot of surface area, so it can collect a lot. But it happens in three distinct stages. I'll go ahead and give you a little rundown of this. For an old dead star, now the yellow is the location of iron. You have your first, second, and last stage. And the black, just ignore the black. That's just the entire structure. I did this with the good old MS Paint back in the day. This paper is dated, there's no date on here. I think I did this in 2018 or 2019, can't remember. But you have the first stage, and that's when the iron collects in the very center. Your second stage is where it collects, but it combines with other elements, making molecules and iron ore and stuff like that. And the very last is a lot of iron ore leftovers, and then you can find meteorites on the surface and various other things that came from outer space that haven't actually burned up completely. And I'll read this out to you. I know there are lots of people out there that would rather me read it to them than read the paper. So here we go. Of course, I'll link this to the bottom. Hi, Celeste. Stars deposit iron in three basic levels. First, they form the core in a very pure form alloyed with nickel. Second, once that inner iron core is formed, material then deposits that is chemically combined with the iron forming molecules. Third, any more deposited iron lands on the surface as meteorites. This shows how different the star was throughout its metamorphosis. So the fact that Earth has a huge iron nickel core, Mercury, Mars, Moon, Venus, the fact that they even have those things tells us a lot of information, what we need to know about the oldest stars in the universe, the oldest stellar remains, the oldest asteroids, if you will. To form a core, something as large as Earth's inner core, made up of almost completely pure iron and nickel, we need to realize that the iron has to be too energetic to form chemical compounds. This energy is provided by the star when it is very young. What I mean to say is, to form a pure iron and nickel in such a huge amount, you can't have given it the possibility of forming with other elements making compounds. If there was oxygen in the way, the oxygen would have combined with the iron, making iron oxide. The fact that it's pure iron and nickel means that iron, when it formed in the center, was so freakishly hot that no amount of chemical reaction or chemical combination would allow it to form the molecules. It was just too energetic. So it just collected in the center. The purification process of the vast majority of incoming material towards a star is done with the star's extreme and external and internal heat, as well as its strong gravitational attraction. So the object that makes the iron extremely hot and prevents it from combining with other elements, making molecules, is the star itself. That's what purifies the incoming material from asteroids. No matter what composition an asteroid is, no matter what composition the small moon was, when it gets absorbed by the star, it rips it apart and purifies it. It makes it so the material can be differentiated. We also know the star is too hot to form molecules at this stage because the cores of really old stars are composed of iron nickel almost in its purest form. If it was cool enough for chemistry, then there would be molecules formed on large scales which exist in the ores. So we can tell how much cooler the star had to get, depending on the types of chemistry that happened inside the iron ores. And those specific ores are different combinations of iron and oxygen, iron and sulfur, iron and what have you. The second stage of iron deposition happens as the middle-aged star collects lots of interstellar iron which slams into the Earth when it was more about Jupiter-sized. The iron supplied will not be able to be purified and then immediately deposited because it is not hot enough in the gas stages of the star's metamorphosis. But it will break apart enough molecularly to combine with other elements that form the mantle and crust. These chemical compounds and molecular structures are called hematite, magnetite, limonite, marcasite, pyrite, siderite, and my childhood favorite, fool's gold, which is pyrite. Pyrite is sulfur and iron combined together, making those big cubic crystals. And that stage happens towards the middle. That's what forms the majority of the mantle material. If there's iron there, the iron will be not in its pure form because it won't be energetic enough to be in its pure form. It'll have cooled down and combined with the other elements. And that happens during gas giant all the way down. Gas giant, more like gray dwarf, which is a bit bigger than Jupiter, or I think smaller than Jupiter. Yeah, smaller than Jupiter, and maybe Jupiter sized, all the way down to past Neptune, maybe even middle ocean world stages. But then once that crust starts to form, you get these types of things. Of course, inside the very deep ocean world, you get these huge iron banded formations, and these formations signal that it took time to form. So these formations right here where there's iron, that's from the incoming material from outer space. It's been spread out over the entire crust of the newly forming Earth. But this material is essentially an extremely old seabed, long before there was even life in its current form, and the Earth had a very thick water ocean slash ammonia type atmosphere, similar to Neptune, all the way down to late stages of the ocean world stars. But yeah, there's that. This thing I think is 2.4 billion years old. So this formed when the Earth was around 2.1 billion years old, about double the age Neptune and Uranus are right now, but definitely not old enough to where it had life on its surface, because it didn't have a surface. It was an ocean world. Let's see what else here. After the core is formed and after the majority of the iron ore is already chemically combined, asteroids that enter in the Earth's atmosphere just break apart in the high atmosphere and land on the ground or in the ocean. They can be picked up off the ground and examined. They will never be able to reach the core as fully ionized material. As well, will never combine enough with the atmosphere on large scales, forming ore deposits that can be mined. Iron ore deposits were formed long before Earth even had a crust that we are familiar with, as they composed the crust itself. So the fact that we have a crust now, and the idea that it's formed via the rock cycle is totally incorrect. The crust was formed when the material that composed the crust was formed, many billions of years ago. It is only logical to realize that the crust cannot exist before the material that composes it even appeared. Well, that's obvious. As well, the core is formed long before the crust, covered in the CBC principle, or core before crust principle, based on the geological principle known as superposition. Now, I don't know if you guys know about this principle. I drew it up back in 2015 or 2016, if I remember correctly. But the CBC principle means core before crust. So, in order to form something as massive as the Earth, and as massive as Mercury or Mars or Venus, you had to have formed it inside out. Because the core just doesn't, you just don't form the whole body and then put the core material in there after the fact. That would be like building a house and starting with a roof first, and then placing all the building materials on top of the roof, and then the materials that are on top of the roof to build the house suddenly seep through and then make the columns to support the roof, that make the concrete ground, that all the pipes come in. No, if you're going to build a house, you start from the foundation up, and then you put the roof on last, and that's what the crust is. So the core, think of the core as the structure to the foundation of the house, or a large skyscraper, if you will, and then you build on top of that after the fact. So that's in line with the geological principle of superposition, meaning as you layer material, the younger the material is, the higher and higher it is. So when you go deeper inside the Earth, the older and older and older you get. This means the cores of these ancient dead stars are the oldest structures of the stars themselves, which is, well, pretty obvious to me, but I don't know. A lot of astronomers and geologists, that sort of just right over their heads. So what we have here are three distinct stages to land and earth formation concerning iron. We also look at the iron ore deposits to determine what the atmosphere of the earth was like during those periods. The fact most of the surface iron has combined with oxygen is telling, and in the case of limonite, which is hematite and water, we can tell how much water was in the vicinity. There's that. And then, let's see, last not least, says here, yeah, I think that basically sums up that part. I was going to do another talk on iron and nickel being leftover catalyst. I guess I could review that a little bit. This paper right here, I'll talk about that later, but basically all I went over was to make a lot of the chemical reactions that happen inside the star as it evolves. The iron and nickel that are entered in through the atmosphere and that collect in the center, they function as catalysts. And a catalyst is something that speeds up or I guess it could slow down, but makes a reaction easier to happen. And the catalytic material is the iron, and a lot of the catalytic material, those unconsumed inside of reactions, sort of just fell towards the interior. And we know it's